Hey everyone, Chris here. Sorry for the delay in getting this up. Just tied up a little bit and just unable to do so. So I'm going to make it really quick. It's short. There's not much to it, and then we can go over some of the problems. I do want to encourage you to do the practice problems at the end, much like the others. So we've talked before that we have. Humans have 23 pairs of chromosomes. And remember, those 23 homologous pairs, they come as 22, which are autosomal, and the the last pair, the 23rd pair, are your sex chromosomes. And so essentially we identify those as the X and the Y. In females, the sex chromosomes are XX, so in a sense they are a homologous pair. And in males, you have one X and one Y chromosome, and they are non-homologous. All right. And we've done this a little bit already, so hopefully this is just kind of a quick recap. But if we look at a Punnett square and we talk about sex determination in sexually reproducing organisms, the male having, although when we talk about genotypes, okay, in the past we talk about genotypes as the types of alleles present, types of alleles for an individual. And we might use various, individual. And we might use various letters like we've talked about, big T, little t, or big A, or whatever. And these really represent genes on chromosomes. But when we talk about sex determination, we're actually using the chromosomes. So for a male, right, we would actually use X and Y, and these represent chromosomes. All right, in a moment, we're going to talk about specific genes that are on the sex chromosomes, and then we'll go back to using that same kind of notation where we use, so for example, a particular trait on the X chromosome might be shown as, so X being the X chromosome, and then, a particular letter to represent a specific gene or specific phenotype for a gene on that chromosome. So when we look at the possible male gametes, so again, much like any other pair of chromosomes, the sex chromosomes segregate during metaphase of meiosis 1, and so a male could produce sperm that are carrying an X chromosome or sperm that are carrying a Y chromosome. So these would be the gametes that the male produces. The female produces eggs that because she has homologous pairs of chromosomes, the eggs that she produces are always X. So you probably heard that before in terms of the male determining the gender of the offspring because the male donates either an X or a Y. So here we can see the combinations, and just like we've talked about with the toss of a coin, the chance of having a boy or a girl are 50-50 in this scenario. And we could, like we've talked about, just sort of scratch out that row because it's just a repeat of the same gamete. And so we can see there's a 1 in 2 chance of producing a girl and a 1 in 2 chance of producing a boy. And that's pretty straightforward. And as far as sex determination is, that's it. But what we're going to discuss a little bit further is what we've talked about before. There are other genes on the sex chromosomes that determine traits other than sex or sex-related traits. And these are referred to as, sorry, I had to pause my microphone as I was about to sneeze all over the place. These are called sex-linked traits. Okay. Again, they're not traits to do with sex characteristics or gender, but because they're on the X chromosome, we refer to them as sex-linked traits. Okay, so let's have a look back to our fruit flies. We talked about other questions before involving the color of the body of the fruit fly being ebony or yellow. Another trait in fruit flies is the color of their eyes. And maybe you've seen this as, you got the pile of fruit in the bowl over several days, and all of a sudden there's fruit flies there. Not that they've generated spontaneously, but they definitely hone in on the ether smell. So there's a bit of a release of gas from ripening fruit that attracts those flies there, and so they reproduce like crazy. And a specific sex-linked trait is eye color. And so in this case, eye color is a sex-linked trait, and we would show it as a capital R because red is dominant to white. So this is red eyes, and X lowercase r is white eyes. One of the most important things with respect to genetics problems using for sex-linked traits is you must show the actual chromosome as well as the allele. Okay, so the allele for red eyes we use capital R, the allele for white eyes we use lowercase r, and that's because it is a dominant trait. So red is dominant to white. Okay, so running an example of a problem involving sex-linked traits. What does a Punnett square look like for sex-linked traits? Construct a Punnett square for a female with white eyes crossed with a male for red eyes. So just like any other problem, number one, we identify genotypes of parents. So for the red it says a female with white eyes. So the female is white. She has to be both X's. And because she's white, which is homozygous recessive, right? Because white is recessive to red, her genotype would be big X, little r, big X, little r. Crossed with a male that is red eyes. Well, a male is XY, so he has only one X chromosome, and if he has red eyes, then it is capital R. All right, so we can fill in our gametes in the table up above. If we put the female on the left-hand side, male across the top, so we'd have X little r, and we could do the bottom row, but again, I'm going to say there's no need to repeat if the gametes are the exact same. Whereas with the male, we have an X with a big R, and we have a Y. So our possible offspring become big X with a big R, big X with a little r, and we have big X with a little r and Y. And so what are the genotypes and phenotypes of the offspring? So our answer here, I'll just change colors. So we would have a genotype of big X, big R, big X, little r, which would be red-eyed females. Okay, so what we've got here is didn't really change the color of my pen, did I? But we've got genotype followed by phenotype. And the other genotype, big X, little r, Y, which would give us white-eyed males. All right. That's a very simple problem, just sort of showing you the notation to use. Interestingly, the gene for color vision is also sex-linked trait in humans. I should say it's making a comparison here that, fruit flies have color vision like us. Fruit flies, I'm not sure their vision, but the gene we're talking about is just the color of the eyes, red or white. We have a gene, humans, on our X chromosome that gives us the ability to detect color vision, right? I wanted to do this in class, but I think this would be a fun activity just for you to check out on your own. Sorry, I've got that in the way, but so you can do a little test for yourself to see if you can see all those numbers. We'll talk about it in class on Monday. But just like with the any other sex-linked trait, you can see this in different ways expressed. So they might use a capital N for normal vision and a lowercase n for color blindness. And sometimes you might see a capital C and a lowercase c. I don't like that one so much because the letters look the same, right? So N for normal, lowercase n for color blindness. So for example, we could have a female who has normal vision but is heterozygous. This is an important distinction to make when we're talking about sex-linked traits, because this indicates a female that is what we call a carrier. So she has normal vision, but when an individual is heterozygous for that specific trait, we refer to them as a carrier. So that would be that female would have normal vision but carry the gene for color blindness. Interesting thing with males is that, and it's why sex-linked traits show up more often in males, because they don't have the alternate X chromosome to mask the recessive allele. So if they have the recessive allele, they only need one in order to see the phenotypic appearance of that trait. So that's it. There's some questions here at the bottom. And again, I apologize for that being a little bit late. Enjoy the rest of your weekend. See you Monday.